This video, we're going to walk through the CYU question that gave us a trig function that describes the voltage of an electrical circuit, and we're given a formula, and T is measured in seconds. And basically, in this problem, we've been asked to go through and identify the key features of this function, this periodic function, what they represent within the context, and then answer some other questions about it. So just before I even begin, I like to sort of go back to what we know about the key features of our trig function and, sort of the basic form. So in general, if we had, I'm just going to make sort of a note to the side, if I had f of x, I'd have, an a value cosine b x minus c, and then plus d. And I sort of ran out of room there, but that's okay, you get the idea. Now, if I go and look at this particular function that I've been given, I'll notice right away, okay, I got a 3.8, so that corresponds with the a value. And then the only other number that I see that sort of represents similar to what I have over here is I do have a b value, and that would be the whole 40 pi. But there's no C and there's no D. And so what that's telling me is I don't have a horizontal or vertical shift going on in this particular function. The midline would be 0, because if we remember the vertical shift, that D value, that's another, that's going to tell us where our midline is. And since technically, I could think of it as a plus 0, my function's midline is at 0, which isn't a question that's being asked, but I like to think about all these things before I sort of dive into the nitty-gritty details. Okay, so we remember that A right here, remember A? Not only does that tell us sort of our vertical stretch or compression factor, it also gives us the amplitude. And so in this case, the amplitude of the function is 3.8 volts. And so what a 3.8 in this particular context is doing is it's telling us basically that the voltage is going to oscillate or sort of go up and back 3.8 volts above and 3.8 volts below the midline, which in this case, remember we said that that midline was a voltage of 0. And so we can say that the voltage oscillates, and oscillates is just a fancy word for, fluctuates. You could also use the word fluctuates between negative 3.8 and 3.8 volts. And we know it's between, so it's another way to think of it is 3.8 above and 3.8 below that sort of middle value. All right, so next we're asked to determine the period of the function and explain its meaning. Now remember, our actual formula doesn't give us the period. Instead, we have that sort of b value, that angular sort of frequency that sort of talks to us about sort of how quickly are we moving through things. Now, if I want to take from my b value to get into, so in this case, our b value is 40 pi. There's b. And so to get to our period we find by saying, okay, well, normally it would be 2 pi. And if we divide that by b, we're going to figure out how long one cycle of our function is. So in this case, 2 pi divided by 40 pi. The pi divided by pi is equal to 1. And so I'd really just be left with 1/20th, or if it helps you, you could think of that as 0.05 as a decimal. And so basically, in this particular, what this is telling me, this is time. So remember, period is your input value. And so in this case, that's how long the voltage takes to make sort of one cycle. So the voltage makes one cycle in 1/20th of a second. So it doesn't even take a full second. So then if you're asked to figure out the frequency of this function, so the frequency, remember, if in case it's been a little while, is 1 over the period. And so in this case, that's 1 over 1/20th, which is actually 20. And this is basically what the frequency is telling us is in 1 whole second, this voltage is going to complete 20 cycles because it completes it takes 1/20th of a second to do one cycle. So in 1 full second, it would make it through 20 cycles. So I'm going to just write that out for you. The voltage makes 20 cycles in 1 second. All right, so if I'm now thinking about my function, how many times in a second will the voltage in this circuit be negative 3.8 volts? Now, basically, this is asking us not to solve an equation, but basically just to think about how many times will this function pass this particular output value. Now, let's take a minute and just think about this function. So this is a cosine function. And if you remember, cosine functions start high, go low, and come back high again. And if we remember in this particular case, our midline's at 0, so our function's not been moved up or down, but it has been vertically stretched by 3.8, which means the max of this function is going to be 3.8, and the min of this function is going to be negative 3.8, because remember we talked about how the voltage oscillates between negative 3.8 and 3.8 volts. So we're basically saying in how many times will we hit this minimum value in 1 second? Well, we know that it makes 20 cycles in 1 second. And in one particular cycle through, it only hits that minimum value once. So we're going to have, it's going to hit that point 20 times per second. And that's, once per cycle. And that's because this is a minimum value and our voltage is only going to hit the minimum once in one rotation. For the next part, we're going to actually jump ahead to G and come back to E and F because I think it will make a little more sense when we look at the graph and sort of explaining the thinking of how do we approach E and F. Now, obviously, I would check my graph in Desmos for this, but I still want to go over just sort of how to set up a graph to make it look nice if I'm sort of sketching a graph for a contextual problem. So I'm going to start with my axes. And I might as well use the line tool since I have one. So I have my vertical axis and I have my horizontal axis. And whenever we're making a graph, you really want to make sure, one, we label our axes, and then two, put values on them. That's always an important thing. So in this case, remember our horizontal axis, if we sort of go back to the beginning of our problem, we remember that t is measured in seconds. So this is going to be time, and we'll just say in seconds. And then our vertical axis is voltage. And I already know, we sort of discussed this, it has a max value of 3.8 and a minimum value of negative 3.8. Because remember, we talked about the amplitude and that it was fluctuating above, 3.8 above the midline and 3.8 below the midline, and the midline is at 0. Now, normally when I'm sort of graphing trig functions, my next step would be I would, sketch in my midline, but I don't, my midline's 0, so I don't really need to sort of put that in the graph, but in case you want to, we'll put in our midline. So there's our midline, and we're just going to label that, midline at y equals 0. And then I personally also like to graph sort of where the max and the min would be. So we have our max values, it's around, 3.8, and I'm a little off there, so I'm going to just sort of shift it. And then our min is at negative 3.8. And so I sort of have like, guides to which to keep my function between. And then I'm starting with a cosine function. Cosine starts high. So I know for sure I'm going to be starting at my maximum value. And then one full cycle later, I'm going to be back at my maximum value. And so in this case, I actually want to sort of think about what is the cycle. Well, we said the cycle is 1/20th of a second, which is 0.05. So I'm just going to go over here and I'm going to mark 0.05. That's going to be one full cycle. So I'm going to be back at that maximum value at the end of my cycle. I also know that halfway through this cycle, I'm going to be at my minimum value. So I'm going to sort of go in here and I'm going to make up a point that's halfway. And, halfway would be 0.025. And at a halfway point, I'm going to be at my minimum. And then here's the neat thing about trig functions. Halfway, if you think about sort of your circle and your circular motion, cosine here, my horizontal distance is at 1. And then over here, my horizontal distance is at -1 in a normal circle that's not been stretched. But then halfway between that, we hit where the horizontal distance is 0. And so halfway between my sort of one cycle, so a quarter of the way through my cycle, I'm going to be at sort of 0. And that gives me then sort of like a rough, on my midline. And that gives me a rough guide to sort of connect. And remember, initially we are increasing at a, or, our horizontal distance is, getting smaller at a decreasing rate. And then, we switch and we're still decreasing, but now we're decreasing. Our horizontal distance is decreasing at an increasing rate. Now we're increasing at an increasing rate and then increasing at a decreasing rate. I'm mixing up my rates of change. My graph is correct. My verbal description was a little messed up there. And I like to sort of continue it on a little bit into the next periods, just so that it doesn't quite just look like a U or a V. You can sort of see the curve and where it would continue. Now, why I wanted to draw it sort of this way, and I actually may continue this on for the next period because it's going to help with us going back a little bit. Sort of. That would put us back, back at our minimum, and so halfway would be there. All right, so I'm just sort of giving myself a little bit extra. And the reason I'm doing that is if we sort of go back to this problem right here, we're being asked to evaluate at 0.04. So, that's a number pretty close to 0.05. This particular problem, you would just input this into your calculator. So, to evaluate this, you're going to put 0.04 in for t. You do want to make sure that your calculator is set in radian mode, not in degree mode, or you will get the wrong answer. So it's times. And if you do, you should get around 1.174 volts. Now, if I think about that on this graph, that would be, we're going to just sort of, maybe a point like right here. I'm just eyeballing this. Now, keep in mind, this is exactly 0.01 below our maximum value. Now, the nice thing about trig functions is they're very symmetrical because we have this sort of circular motion going on. And so if we're, this much below, that max value, then, the same thing's going to be modeled in the next quadrant over. And so you can sort of, think about, okay, we're going to have a matching point at the same solution, same output of 1.174, exactly the same distance away from the maximum, but it's going to be above the maximum. So it's going to be a plus 0.01 above. So when we're asked to determine the next time our output is going to equal the same thing it equaled at 0.04, we're going to know that that's basically going to be where our maximum is. Oops. But we're going to be 0.01 further along. And so that should be occurring when t is 0.06. So at b equals, oops, not v equals, sorry, v of 0.006. Now, if I wanted the next point after that, I could take that original, 0.04 and I could add a period to it. We're going to come back around the circle one full time, at, we're going to come back again at 0.09, and so it's like, there's lots of different times, but, these are just sort of, okay, yeah, we're going to hit that maximum, or so that same output value, looking at that symmetry sort of gives you a sense of it. Hopefully this helps you better understand this particular question.